Okay, so to start with this first problem, we always need to choose what equation do we want to use. In some cases, as we move on, there'll be more options, but in this case, we've given the wavelength, which is 550 nanometers. You have to recognize that wavelength is the variable lambda. So that's our 550 nanometers. And we want to know frequency. That's what we're trying to solve for. Frequency is this variable nu, which looks like v. So that first equation, c is equal to nu lambda, is going to be the appropriate equation. We want nu, so we can solve for that. Again, to solve for that, we'll divide both sides by lambda to get nu by itself. Okay, that will then, on the right-hand side here, that will cancel lambda out, and we'll get c over lambda is equal to nu, which we can then plug into. C is our constant, 3 times 10 to the 8 meters per second. Lambda is our wavelength. And we note that since c is in meters per second, we're also going to need that to be in meters, so that the units are going to cancel out here. We have meters on the top, we're going to need meters on the bottom so that they cancel properly. So in that case, 550 nanometers, again, if we recognize the meaning of the prefix, that's an easy way to get back to base units. Nano here means 10 to the minus 9, so this is 550 times 10 to the minus 9 meters. Again, just recognizing the meaning of the prefix. And at that point, we can just plug that directly in, 550 times 10 to the minus 9 meters, and get our answer. Again, checking our units, meters cancels on top and bottom, and we just have 1 over seconds, or hertz, as our unit here. When we plug that into our calculator, we get 5.45 times 10 to the 14. Significant figures here, we get, say, 3. Maybe I should have put a period there. As long as you're within one significant figure, that's reasonable. In this case, yeah, say 3 sig figs. 5.45 times 10 to the 14, 1 over seconds, or hertz, is our final answer for the frequency. Again, in your calculator, remember to use that E for scientific notation, which will make your life easier. Okay, so take a few minutes to try the next few problems, and after you try them, you can check your answer that I'll show down below. Okay, for number 2, we are given the frequency and want to know the wavelength. So that's the same two variables we used before. C is equal to nu lambda. Now in this case, we want to solve for wavelength. So to solve for wavelength, we're going to divide both sides by frequency, because again, wavelength lambda is what we want to solve for. So divide both sides by frequency. That will get wavelength by itself, and we'll get C over nu is equal to lambda, 3 times 10 to the 8 over, this is meters per second. And again, frequency is in hertz, or 1 over second, so this unit is correct. We're in the base SI unit, which is what we want, so we can just plug in 9.31 times 10 to the 14 hertz. When we do that, we'll get our wavelength. To make the units work out, you can double check this and remember that this is 1 over second is another way of saying hertz. And so keeping track of the units, we have meters per second over 1 over second. So there is a second in the denominator on the top and a second in the denominator on the bottom, which will cancel out. The 1, nothing will happen to that, but we will then get meters as our unit out here. So again, typing that in the calculator, I just have one number in the denominator here, so I don't actually need parentheses. If you didn't use this E key, though, you would need parentheses around the denominator. So again, if you had typed this, again, a mistake I'll see people make is they'll type it in like this, which doesn't work, because what your calculator thinks you mean here is it thinks you mean divided by 9.31 and then multiplied by 10 to the 14th. So you can see the 10 to the 14 here is coming on the top. It thinks you mean this. That's why I think it's just much better to use the scientific notation using that E. If you really don't, again, that's how I would do it, just use the E. If you really wanted to type it like this, you can, but you need the parentheses all the way around there so it doesn't give you the error here. Again, you can also sort of check your answer, just double checking does it make sense by looking at, oh, hey, the exponent here is bigger. This is 10 to the 8th, this is 10 to the 14th. This should be a very small number, the exponents here, right? This is a bigger exponent, so it should be a negative exponent because it's going to be a number smaller than 1 when you take a big number and divide it by this much bigger number in the denominator. Okay, so again, that's 3.22 times 10 to the minus 7 meters. It wants this in nanometers, though, so we need this last unit conversion. So in this case, 1 nanometer is equal to 10 to the minus 9 meter using the meaning of the prefix. So times, I want to go 2 nanometers. We always put the thing that's like desired or the thing that we want over the thing that we have in these unit conversions. So we have meters, so that goes on the bottom. We want nanometers, so that goes on the top. Again, just being careful and rigorous about your units will make this all work out. And here's our final answer. Okay, when we type that in, we get 322 nanometers using 3 significant figures as our final answer. Again, makes sense because we are going from a very small amount of meters to a pretty reasonable amount of nanometers. Okay, now for number 3, this one we have 100 megahertz is our frequency. We want the wavelength. That's the same problem we just did. We're given a frequency. We want to get the wavelength, so it's the same equation. C over nu is equal to lambda. We could resolve that if we wanted to, but we just did it, so we can just plug back in. 3 times 10 to the 8 meters per second divided by, now our frequency has to be in hertz, just like we did before. Since mega means 10 to the 6, that's 100 times 10 to the 6 hertz. Again, or 1 over second as the unit. Again, remember to use proper scientific notation when you're typing all this in, but then you should get. Okay, this one maybe I feel a little bit embarrassed about plugging into my calculator, but I wasn't quite thinking. 3 times 10 to the 8 over this denominator here, 100 times 10 to the 6, that's actually 1 times 10 to the 8. The 10 to the 8s all cancel, and we do in fact just get 3 as our final answer. And we are in base SI units. Always use base SI units when you're plugging into this equation, but this is 3 meters. I don't know about, let's assume that I put a decimal there, so 3.00 meters as my final answer. Okay, for number 4, which type of electromagnetic radiation is the most energetic? You could calculate the energy of each 3 using E photon is equal to h nu is equal to hc over lambda. So using either the wavelength or the frequency, you could get the energy of each photon, but you don't really need to do that. You can use that proportional relationship or inverse relationship. So I'm just using the frequencies there. You could equivalently use the wavelengths. Here are all the frequencies we were given. We solved for this frequency in problem 1. Number 2, we were given the frequency. And number 3, we were given the frequency, but I'm just converting it to hertz, so it matches. Now, if we want to know the most energetic photons, well, without doing the math, we can say, okay, because the equation is E is equal to h nu, This is a direct relationship. The bigger the frequency, the bigger the energy of the photon. And so if I want to know what the most energetic photons is, I need the largest frequency because it's a direct relationship. So that means that our final answer has to be copper. That's the biggest frequency, 9.31 times 10 to the 14 hertz. Again, I can see that here as well. So because of that direct relationship, it's copper, or the answer from number 2. Okay, number 5, if you haven't had a chance to do this one yet, you can try it out, and then I'll show the answer. Okay, so for this one, we are trying to determine the energy of a photon of laser light. So that's what we're trying to find. And again, our given information now is wavelength. We have to just be able to, okay, wavelength, that's the variable lambda. Energy of a photon, that is E photon. And so the equation that we want to go to is E photon is equal to h nu is equal to hc over lambda. Because we're given wavelength lambda, the easiest version of this equation to use is the sort of E photon is equal to this part. So E photon is equal to hc over lambda. That will let us just use these constants, which you can look up, and the given wavelength to get the energy of a photon. Just like in the previous equation, though, we need to make sure this is going to be in base SI units. So we need to go to meters when we plug in there. Okay, so E photon is equal to H is 6.63 times 10 to the minus 34 joule seconds. C is 3 times 10 to the 8 meter per second. Lambda is 1,064 nanometers, but we have to convert that to meters. So 1,064 times 10 to the minus 9 meters. Now, there are a lot of units there, but they will all cancel properly. Meters here will cancel, and we have a seconds on the top here that will cancel this seconds on the bottom. And energy, you should now or a little later in the class really remember that the unit for energy is joules. So that does work out. That will be in joules in the end. Okay, so typing that into the calculator, we get 1.8. What do we get? We get technically 4 sig figs here. I don't know, our constants only have 3 sig figs, so maybe we only get 3, but we'll assume the constants are exact, so we'll go to 4 sig figs, 1.869 times 10 to the minus 19 joules. Very common for these energies in joules to be very, very small because the energy of a single photon is a very small amount of energy. So another unit conversion, in this case we didn't have to do any algebra because the equation came out exactly how we wanted. So here's our final summary of this set of material. We have a couple of our key equations. Speed is equal to frequency times wavelength, with the constants and unit conversions that we might need. And then thinking about the particle properties of light, the energy of a photon is h nu is equal to hc over lambda. Remember to always convert everything to base units, especially converting wavelengths to meters, and use all of the proper calculator techniques to solve these problems. Good luck.